Hello, everyone. Welcome to the first week of CS110 at Virginia Community Colleges. In this chapter, we are going to talk about limitations of computing. Let me go ahead and share my screen with you real quick. In this chapter 18, primarily we'll talk about different chapter goals and limits on arithmetic components, communications, etc. We'll talk about complexity of software, software engineering, then formal verification, open source movement, notorious software errors, comparing algorithms. We'll talk a little bit about big O analysis, Turing machines, the halting problem, the classification of algorithms, and then finally we'll conclude with ethical issues, who am I, and do you know in the slides. So let's begin. Welcome to chapter 18, Limitations of Computing. In this chapter, we'll explore the boundaries that define what computers can and cannot do, limits rooted in hardware, software, mathematics, and theoretical computer science. While computers appear incredibly powerful, every system operates within constraints such as memory size, processor precision, transmission reliability, and algorithmic complexity. Understanding these limitations help us design better systems, write more reliable programs, and appreciate which problems are fundamentally unsolvable. Throughout this chapter, we'll examine arithmetic precision, error detection, software complexity, algorithmic performance, and deep theoretical issues like the halting problem and computability. By the end, you'll have a clear picture of why computing is powerful but not unlimited. In this section, our first set of chapter goals focuses on the ways the hardware and numeric representations are placed. We'll begin by examining how finiteness of a computer storage directly impacts the precision and range of numbers it can represent. This leads to important consequences like round-off errors, overflow, and underflow. Next, we'll explore how computers detect errors and when transmitting data, a critical part of communication reliability. Finally, we'll identify limits imposed by software itself, including issues related to representation and design. These goals establish the foundation for understanding why computing cannot deliver perfect accuracy or infinite precision. Instead, computer scientists must work within these constraints and develop strategies to mitigate or manage inherent limitations. The second set of chapter goals, we discuss ways to build better software, and the goal moves beyond hardware and software limitations to the deeper questions of computability itself. We use engineering approaches, testing techniques, and formal verification to build a better software. Beyond that, we examine the limits that exist even when perfect hardware and perfect software, the limits inherent in problems themselves. This includes distinguishing between problems we can solve efficiently, problems we can theoretically solve, but one only with impractical time, and problems that no algorithm can solve at all. The continuum we will explore ranges from the polynomial time problems in class P to NP-complete problems, and finally to unsolvable questions like the halting problem. This framework helps us understand not just what computers can do, but what they can never do. In this slide, we begin our discussion on the limits of arithmetic by examining numeric precision. Precision refers to the maximum number of significant digits a computer can represent. For example, if a computer system supports only 5-digit precision, it can represent numbers within a range such as -99,000 999 to positive 99,999. This restriction arises because computers store numbers using a fixed number of bits, limiting how many digits can be encoded. When a calculation produces a number requiring more digits than the system can represent, precision is lost, and the stored number becomes only an approximation. Understanding precision is crucial because nearly every scientific, financial, and engineering computation depends on accurate numeric representation. Even small rounding effects can accumulate into significant errors. What happens if we allow one of these digits, let's say the leftmost one in red, to represent an exponent? When we introduce scientific notation into computer arithmetic, we increase the range of representable numbers at the cost of fewer significant digits. In this slide, we imagine reserving one digit, such as the leftmost digit, to represent an exponent rather than part of the value. For example, the notation 3245 multiplied 10 raised to 3 represents a large number while still only using a small number of digits. This approach allows computers to store extremely large or small values by encoding mantissa, and an exponent. However, because we now devote one position to the exponent, the number of digits available for the mantissa decreases. As a result, we gain range but lose precision. This trade-off forms the foundation of floating point representation used throughout modern computing. The range of numbers we can now represent is much larger. Here we see how using an exponential notation dramatically increases range of representable values. With 4 digits of significance and 1 digit reserved for the exponent, a computer might represent numbers from negative 9,999 times 10 to the ninth power all the way up to the positive 9,999 times 10 to the ninth. While this extended range is powerful, only 4 significant digits remain accurate. Significant digits are those between the first non-zero digit on the left and the last non-zero digit on the right. Any digits beyond that are simply not stored. This means that operations involving large or small numbers can result in rounding or loss of detail. Engineers and programmers must keep these precision limits in mind to avoid misleading results. Limits on arithmetic. This slide expands on consequences of limited precision. With only a fixed number of significant digits available, a computer must truncate or round the number of remaining digits, effectively assuming they are zero. This means that 4 leftmost digits of a number remain accurate, but everything beyond them is lost. As a result, computation involving numbers with many significant digits can suffer from accuracy problems. For example, adding two very large numbers or subtracting two numbers that are close together may lead to the unexpected results. These issues aren't due to programming mistakes, but rather the fundamental constraints of binary floating point storage. Recognizing when precision loss may occur allows developers to choose algorithms that minimize these errors or use alternative numeric formats when necessary. To represent real numbers, we extend our coding scheme to represent negative exponents. This enables values such as 4.394 multiplied 10 raised to minus 2 equal to 43.94, or 22 multiplied 10 raised to minus 4 is 0.0022. Negative exponents allow computers to represent numbers much smaller than 1 without requiring additional digits in the mantissa. This mechanism underlies how floating point numbers encode values across a massive range. However, it also reinforces the trade-off between range and precision. Regardless of exponent size, the number of significant digits in the mantissa still limits precision. Scientific notation is a powerful tool, but it doesn't eliminate numerical limitations. It simply redistributes them between exponent and mantissa. This slide introduces the sign of exponent and the sign of the number itself. By including a bit digit or digit to represent whether the exponent is positive or negative, and another to represent whether the number is positive or negative, we expand the variety of values we can encode. With this design, we can represent a very large positive numbers, very small positive numbers, and their negative counterparts. The slide asks which values represent the largest negative number, the smallest positive number, and the smallest negative number. Questions that highlight how signs affect ordering in numeric system. Understanding these ranges is essential in avoiding numerical underflow or overflow, which occur when calculations produce values outside the representable domain. In this slide, we encounter several important types of numeric errors. A representational error or round-off error occurs when calculated value has more precision than the machine can store, causing it to be rounded or truncated. Underflow happens when the result of computation is too small to be represented, effectively rounding down to zero. Conversely, overflow occurs when a result is too large for the system's numeric range, causing the value to wrap or produce an error. Another key issue is cancellation error, which arises when subtracting two nearly identical numbers. Because many leading digits cancel out, only small and possibly inaccurate digits remain. This significantly amplifies rounding issues and can compromise the reliability of computations. Here we continue to examine numerical limitations, focusing on two common types of errors, overflow and cancellation error. Overflow happens when a calculation produces number larger than the machine's maximum representable value. When this occurs, systems may trigger an exception, wrap around to a small number, or return an infinity value depending on the architecture. Cancellation error, on the other hand, arises when subtracting two numbers that are extremely close in value. Because many of their leading digits cancel out, only the smallest and potentially least accurate digits remain. This loss of meaningful precision can distort results, especially in scientific or financial computations, where tiny differences matter. These errors aren't due to bugs, they stem from the fundamental mathematical constraints of floating point representation. Recognizing when cancellation and overflow may occur allows us to restructure calculations or use higher precision data types. Integer limits and workarounds. This slide highlights the limitations imposed by fixed word lengths in hardware. For example, with a 32-bit signed integer, the representable range is from negative 2,147,483,648 to positive 2,147,483,647. Any value calculated outside this range will overflow. And it's important to remember this digits, as when you take coding interviews, sometimes it's important to know these numbers to uh, be able to write an algorithm that helps you solve the problem. Let's come back to the slide. These constraints affect any systems using fixed with integer arithmetic. from embedded controllers to large-scale software. However, software can compensate for these limitations. One common approach is representing very large numbers using lists or arrays of smaller numeric chunks, a technique used in big integer libraries found in languages like Python and Java. By chaining together multiple integers, we can represent arbitrarily large values limited only by memory. This slide illustrates while hardware imposes finite limits, software techniques can help circumvent them when higher precision is essential. This final slide on arithmetic section illustrates how extremely large numbers can be represented using alternative data structures. Instead of storing huge number in a single fixed size integer or floating point format, software can break the number into segments, storing segments in separate word or array location. This approach resembles how people write long numbers in groups of digits. Big integer systems perform arithmetic by operating these segments one at a time, carrying digits as necessary. Although this method is slower than built-in arithmetic, it's essential for applications requiring extreme precision, such as cryptography, scientific computing, financial modeling. The key takeaway is that hardware has strict limits. Creative software design can extend numeric capability far beyond machines' native range. So as we see, number A is 752036, and it's represented by a singly linked list by 752036. And example B also shows how it could be done with just storing 3 digits, 752 and 036. And the 036 is the final node of that singly linked list. And example C shows how the summation is done for that singly linked list. If you were to add 83,536 to 41, basically you will be using the last two sections of that singly linked list to add to 1 and 4 and create a new singly linked list to show you the number 3. We can talk about it later in the student engagement sessions if required, but this is an important concept when you take any of these coding exams with any of the big tech companies. Limits on components. Although most errors are caused by software, hardware components also fail. So while software often receives blame for system failures, hardware components can and do fail. These failures may occur due to manufacturing defects, age, overheating, environmental condition, or electrical issues. A failing component can cause anything from minor glitches to catastrophic system crashes. Most modern systems implement a redundancy, error-correcting memory, and self-diagnostic features to mitigate hardware faults, but no component is immune to eventual failure. The slides question whether you have ever experienced a hardware failure highlights that failures are a normal part of computing. Understanding the impact of faulty components is essential for designing reliable systems. Selecting appropriate fault tolerance mechanisms and planning maintenance strategies are important. Error detection and correction. This slide introduces challenges of communication reliability. When data travels across networks, cables, storage devices, or wireless signals, the errors can occur due to noise, interference, or hardware issues. To combat this, computers use error detecting codes, which identify when data has been corrupted, and error correcting codes, which go a step further by attempting to reconstruct the original data. Error detection is essential for ensuring data integrity in applications such as file transfers, memory reads, and network communications. Without these techniques, even small transmissions errors could compromise programs, corrupt files, or derail computations. This slide sets the stage for exploring specific methods like parity bits and check digits that help maintain accuracy and reliability of digital communication. Parity bits. It's an extra bit associated with each byte used to ensure that the number of 1 bits in 9-bit value, byte plus parity bit, is odd or even across all bytes. They are used to detect that an error has occurred between the storing and retrieving of a byte or sending and receiving of a byte. Simplest form of error detection is parity bits. It's an extra bit added to each byte of data. Its purpose is to ensure total number of ones in the 9-bit combination, 8 data bits plus the parity bit, is either odd or even, depending on the system's requirements. With odd parity, the system adds a parity bit to make the total number of ones odd. With even parity, it adds a bit to make the total number even. Parity bits are especially useful for detecting single bits errors during storage or transmission. Although parity cannot correct errors and cannot detect multiple simultaneous errors, it cannot correct errors and simultaneous bit errors. It's fast, it's simple, and widely used in memory, network protocols, and older communication systems. Odd and even parity example. Odd parity requires that the number of ones in a byte plus the parity bit be odd. Here's an example. If byte contains pattern of 11001100, the parity bit would be 1, thus giving an odd number of ones. If the pattern were 4 ones, 3 zeros, and a 1, then parity bit would be 0, giving an odd number of ones. Even parity uses the same scheme, but the number of 1 bit must be even. Check digits and advanced codes. This is a method commonly used in identification numbers such as credit cards, ISBNs, and product codes. A check digit is calculated by summing the digits of number and storing the final digit of that sum alongside the number. For example, in the number 34376, the digits add up to 23. So the number would be stored as 34376-3. This helps detect many common human or transmission errors. More advanced error correcting codes can not only detect errors but also determine which bit is incorrect and fix it automatically. These techniques are essential in applications such as memory systems, satellite communication, and deep space probes, where retransmission may be impossible or impractical. The complexity of software. The problem is complexity. Software testing can demonstrate presence of bugs but cannot demonstrate their absence. As we find problems and fix them, we raise our confidence that the software performs as it should. We can't guarantee that all bugs have been removed. And as projects grow in size, the number of issues that it carries also grow in size. And there is a need for additional layers that can help us maintain the program. The large-scale software development requires detailed software requirements that clearly define what product must accomplish, along with software app specifications that describe its inputs, processing steps, outputs, and special features. These documents ensure that teams share a consistent understanding and that software can be designed with reliability and maintainability in mind. This slide introduces the idea that software engineering is not just coding, it is a structured, disciplined process that supports the entire life cycle of a software system. So, four stages of problem solving are writing the specifications, developing algorithm, implementing algorithm, and maintaining the program. So, moving from small, well-defined tasks to large software projects, we need two extra layers on top of this: software requirements and specification, as we just discussed. In this slide, we'll take a closer look at two foundational software engineering concepts: requirements and specifications. Requirements are a statement of what's to be provided by computer system or software product, and specifications are detailed description of the function, inputs, processing outputs, and special features of a software product. It provides the information needed to design and implement the software. Elaborating on that, software requirements describe what a system must do. They outline the functionality and constraints and user expectations without dictating how the system will achieve them. Specifications take the next step by translating those requirements into a detailed blueprint. This includes the system's inputs, how data will be processed, expected outputs, and any special features or conditions. Specifications serve as the contract between designers, developers, and stakeholders, ensuring everyone shares a common understanding of the solution. Together, these two elements form backbone of structured software development. Without clear requirements and well-written specifications, project risk miscommunication, inconsistent design choices, and costly errors later in the development cycle. Next one is testing techniques. Testing techniques have been a running thread throughout the book. They are mentioned here again as a part of software engineering. It is woven throughout the software development process. In fact, Bill Gates used to say that Microsoft is a testing company because more than half of the staff at Microsoft continuously tests their software. Anyway, two techniques mentioned are walkthroughs and inspections. A walkthrough is an informal review where developers present their code or design to peers, explaining the logic step by step. The emphasis is on understanding, early detection of errors, and team learning. Inspections are more formal and structured. They follow a documented process in which reviewers examine code or documentation line by line, searching for defects against predefined checklist. Inspections are highly effective at catching issues before testing even begins. This slide highlights that effective software engineering combines multiple testing approaches, each contributing to higher confidence and better quality software. Testing is not just finding bugs, it's understanding the system deeply and preventing defects early. The final slide on software engineering addresses unavoidable reality of software defects and sets expectation for typical error rates. Standard commercial software might contain around 25 bugs per thousand lines of code. Well-engineered, high-quality software may reduce this to around 2 errors per thousand lines. The extraordinary engineering behind space shuttle software drove defect rates even lower, fewer than 1 error per 10,000 lines of code, through rigorous methods and exhaustive testing. These comparisons show that quality is not accidental. It is achieved through careful processes, disciplined engineering practices, and continuous verification. Even then, perfection is unattainable. The purpose of tracking defects density is to set realistic goals and make informed decisions about testing cost and reliability. The slide reinforces that reducing errors is about managing complexity, not eliminating it entirely. Formal verification. This slide introduces formal verification, a rigorous techniques used to prove program correctness mathematically. Unlike traditional testing, which checks behaviors with specific inputs, formal verification analyzes algorithms and logic to ensure correctness for all possible inputs. These methods are especially valuable in safety critical systems such as aerospace, medical devices, and chip design. Formal verification has been successfully applied to hardware, including the design of computer processors and communication circuits. The hope is that over time, these techniques will extend more fully to complex software systems. While formal verification is powerful, it's also resource intensive and challenging to apply to large, rapidly evolving code bases. Nevertheless, as software becomes increasingly mission critical, formal verification offers a way to improve reliability where failure is not an option. Open source movement. Here's a brief history of open source movement. Before the 70s, source code was typically distributed with computers and programmers freely modified and shared improvements. As the software industry matured, companies began withholding the source code to protect proprietary products. Later, with the growth of internet, open collaboration reemerged as a powerful development model. Many modern open source projects rely on community contribution, peer review, and central coordinator, sometimes referred to as a benevolent dictator, to guide direction. The Linux operating system is one of the most well-known examples of open source success. This slide highlights how the movement revived the collaborative spirit that marked the early days of computing, enabling innovation through shared knowledge and community-driven development. Continuing the discussion on open source software, noting that many companies now treat open source development as legitimate and strategic option. Studies have shown that open source projects often have lower defect rates than commercial software, thanks to constant peer review, transparency, and community engagement. However, open source is not immune to significant vulnerabilities. The slide references the well-known Heartbleed flaw discovered in OpenSSL in 2014, a vulnerability that affected major websites and systems around the world. This example illustrates both the strengths and the risks of open source development. While many eyes can improve security and quality, critical components may still suffer from underfunding or limited oversight. Open source remains key pillar of modern computing, balancing openness with the challenges of maintaining high-quality community-driven code. Notorious software errors. AT&T down for 9 hours. Here we recall a major software failure that occurred in January of 1990 when AT&T's long-distance telephone network crashed and remained down for 9 hours. The failure was traced to subtle software error introduced during an upgrade to the company's electronic switching systems. When one switch rebooted and returned online, it sent a message that triggered a flaw in other switches, causing them to crash as well. This cascading failure demonstrated how software errors in large systems can have wide-reaching and costly consequences. It also highlights the importance of robust testing, fault-tolerant design, and careful deployment procedures. The incident remains a classic example of how a single software bug can disrupt essential infrastructure relied upon by millions of people. Another example is the Mariner 1 Venus probe. We know the infamous failure of NASA's Mariner 1 Venus probe, launched in July of 1962. Shortly after takeoff, the spacecraft veered off course and had to be destroyed to prevent potential danger. The root cause was eventually traced to a tiny typographical error in Fortran program. A period was mistakenly typed instead of a comma in guidance equation. This subtle error eliminated a smooth function that stabilized trajectory calculations. As a result, the rocket received erratic guidance signals, ultimately leading to mission failure. The loss amounted to $18.5 million, an enormous sum at that time. This incident underscores how small software mistakes can have massive consequences, especially in mission-critical environments. It's a powerful reminder of why rigorous review and testing are essential in aerospace and other high-stakes systems. Comparing algorithms. Here we have a figure showing equally valid solutions to the same problem. Multiple algorithms can solve the same problem but may differ dramatically in efficiency. The figure shows two valid algorithms for a task, emphasizing the idea that correctness alone is not enough. Performance matters. Two programs may produce identical results, but one might run significantly faster than or require fewer resources. Algorithm design involves choosing the approaches that balance clarity, correctness, and efficiency. This concept is foundational to computer science and leads directly into the next set of slides, which introduce big O notation. By comparing algorithms, we gain insights into how solutions scale as the size of input increases, helping us select the most practical and effective method for real-world applications. Big O analysis. We use a spatial notation to compare algorithms, a notation that expresses computing time complexity as the term in a function that increases most rapidly relative to the size of a problem. It's a mathematical framework used to compare efficiency of algorithms. Big O describes how the time or space requirement of an algorithm grow relative to the size of the input. Rather than giving exact runtimes, Big O focuses on trends, identifying dominant term that increases most rapidly as the input grows. This abstraction allows us to compare algorithms across different machines, languages, and implementations. Big O is essential for understanding how algorithms scale and predicting performance on large data sets, whether analyzing, sorting, searching, graph, traversal, or numerical computation. Big O gives us a shared vocabulary for reasoning about complexity and choosing more efficient designs. Here we see we identify the dominant term in a function when applying big O notation. Consider the equation f of n is n raised to 4 plus 100n squared plus 10n plus 50. As n grows, the n raised to 4 term increases far more rapidly than others. This means that for a sufficiently large value of n, the lower order terms and constant terms become insignificant. So we say the function O is O raised n raised to 4, O of n raised to 4. The big O focuses on the long-term behavior, not small early values. This abstraction helps us evaluate algorithm independently of hardware differences or temporary fluctuations. The key insight is that only the term with highest growth rate determines the big O classification. Understanding this principle is essential for analyzing algorithmic performance and making decisions about scalability. In this slide, the concept of dominant terms is explained through a memorable analogy. If you are buying both an elephant and a goldfish, only the price of elephant matters when comparing costs between the vendors. The goldfish's price is negligible in comparison. Similarly, the function we discussed in the earlier slide, n raised to 4 term is the elephant. It dominates the total of the large values of n. The smaller terms, like goldfish, contribute so little to the final outcome that they don't influence the big O classification. This analogy reminds us not to get distracted by small details when analyzing growth behavior. Big O allows us to simplify complex expression by focusing on what truly drives the computation cost. Here are the most common orders of magnitude. O of 1 is called bounded time, assigning a value to the ith element in an array of n elements. In a simple language, it would be just that we are passing through the code just once, O of 1. There are probably no loops making it go through certain equations multiple times. O of log n describes logarithmic time algorithms, which repeatedly divide the problem size in half. Binary search is a classic example of O of log n performance. These categories form the foundation of algorithmic analysis. Understanding them helps developers estimate how performance will change as data grows. Small differences in big O orders can translate to dramatic real-world effects when systems scale. This slide sets the stage for examining more complex classification in the next few slides. O of n square is called quadratic time. Algorithm of this type typically involve applying a linear algorithm n times. Most simple sorting algorithms are O of n square algorithms. Similarly, O of 2 raised to n is an exponential time, as the numbers would increase in an exponential manner. And O of n factorial is a factorial time, as numbers would increase as the n increases. The traveling salesperson graph algorithm is a factorial time algorithm. O of n square is a quadratic time where linear processes must be repeated n times. Many simple sorting algorithms like bubble sort or insertion sort fall into this category. These classifications highlight the vast range of algorithmic efficiencies and demonstrate why certain methods are preferred when handling large data sets. Here is a comparison rate of growth numbers, and we can look at the numbers for each of those algorithms that we just discussed. And especially we can see how 2 raised to n becomes a really big number really fast. And you wouldn't want an algorithm with that kind of big O. And this analysis is important from the career perspective, as a lot of this big tech, when they ask you a coding question, this will be one of the points that you discuss when you solve the problem in front of them. And basically, you try to show them that you can come up with a solution that is lower time complexity in general and the best solution possible for the given problem. From the previous slide, as we know that exponential and factorial grow really fast, of and factorial algorithms grow at a rate far beyond exponential in this slide. A well-known example is traveling salesman problem, where evaluating every possible path through n cities require n factorial computations. These classes illustrate problems that escalate beyond what any realistic system can handle. Understanding these growth rates helps us developers recognize when brute force or naive solutions are unacceptable, motivating the use of heuristics, approximations, or better theoretical approaches. And the next slide is a final overview of complexity of the classes using the chart labeled orders of complexity. It visually reinforces how each class grows relative to others. As you move from O of 1 to O of n factorial on the chart, the required resources escalate dramatically. This message is clear. Choosing efficient algorithm is essential. This summary slides wraps up the big O section by reminding us that complexity isn't just academic. It directly impacts scalability, performance, and feasibility. An algorithm that works for small inputs may become unusable when dataset reaches millions or billions of elements. Big O provides the framework for predicting and managing that behavior. Turing machines, the Turing machine model. A theoretical model developed by Alan Turing in 1930s became very popular. There is even a movie on that. You should look it up if you haven't. A Turing machine consists of a control unit and a read-write head that moves along an infinite tape. The tape is divided into cells, each holding a symbol. Based on the current symbol and machine state, the Turing machine can write a symbol, move left or right, and change states. Although simple, this model captures the essence of computation. It provides a foundation for understanding what problems can be computed mechanically. The Turing machine is not a physical device, but a conceptual tool that helps computer scientists explore the limits of computability and algorithm design. Why Turing machines matter. The strength of Turing machine lies in its universality. It is widely accepted that anything intuitively computable by a real machine can be computed by a Turing machine. This idea forms the basis of the Church-Turing thesis. If a problem can be solved algorithmically, a Turing machine can do it. Conversely, if we can prove that no Turing machine algorithm exists for a particular problem, then that problem is unsolvable by any computer. This insight allows researchers to classify problems not just by difficulty, but by fundamental computability. The Turing machine serves as the theoretical yardstick for what computers can and cannot achieve. The halting problem. One of the most famous concepts in theoretical computer science, halting problem asks, given a program and an input, can we determine whether a program will eventually stop or continue running forever? At first, this may sound like a problem we should be able to solve with a clever analysis. However, the halting problem is known to be unsolvable. No algorithm can correctly determine halting behavior for all possible programs and inputs. This result has profound implications. It shows that there are inherent limitations to what computers can analyze or predict about their own behavior. The halting problem marks the boundary between solvable and unsolvable computational questions. Assume that there exists a Turing machine program called solves halting problem. It remains any program example and input sample data where the program example halts given input sample data. We imagine a Turing machine. This program supposedly takes two pieces of inputs, another program called example, and a specific input of that program called sample data. The hypothetical solver would then output either halts if example eventually stops, or loops if it runs forever with that input. This setup is purely theoretical because the next slide will show that such a solver cannot exist. However, constructing this hypothetical tool is essential for proving the halting problem's impossibility. By assuming the solver exists, we can show it leads to logical contradiction, hereby proving no such universal programs can ever be created. So here is the similar slide where the first input becomes program example and program example over the iterations, trying to solve the halting problem. And the output always remains halts or loops. So target program and input data were supposed to be the inputs. It then processes how to determine whether the target program halts or loops indefinitely. This is the structure of a Zoom solution. By formalizing the idea, we can analyze its behavior more precisely and identify the contradiction that proves the halting problem is unsolvable. The slide prepares us for the construction of new program that exploits the assumed solver, ultimately showing that any such solver leads to inconsistent results. Now let's construct a new program called new program that takes the program example as both programs and data.